Gradient descent lets us minimize the value of the function by iteratively determining new inputs that minimize it. We will now consider the technical details of how the gradient descent works, and then do an example where we minimize functions using gradient descent. Before we consider the formula for gradient descent, we should consider its component functions. First, is the derivative. When the derivative of a function at some point x is positive, as we decrease its input, the value of that function decreases. For example, consider the function that squares the input. The derivative of this function will be 2 times the input. When the input to this function is 3, the output is 9. The derivative at that point is 6. Since the derivative at that point is positive, if we decrease the input, the output will decrease as well. When the derivative of a function at some point x is negative, as we increase its input, the value of that function decreases. For example, the value of our function at point -3 is 9. The derivative at that point is -6. And we can see that if we increase the input to this function, the value of the function decreases. In gradient descent, the amount by which we change the input is determined by epsilon. Based on the derivative, whether to decrease or increase the input by epsilon is determined by the sine function. When the input to the sine function is positive, it outputs 1. When the input is 0, it outputs 0. When the input is negative, it outputs -1. Looking at the formula for the gradient descent, we should now be able to interpret how it works. When the derivative at point x is negative, we increase x by epsilon. When the derivative at point x is positive, we decrease x by epsilon. Let's now minimize a function using this formula. We will try to minimize the function x squared using the gradient descent. We will be using epsilon equal to 0.2, and start minimization with x equal to 1. On the first iteration, we find that the derivative of x squared, at x equals 1, is positive, so we decrease the value of x by epsilon. The new x is 0.8, at which the function evaluates to 0.64. We continue in similar fashion for 4 more iterations, and find that the function achieves minimum at x equals 0. At this point, the derivative equals to 0, so the gradient descent no longer updates our input. It is important to note that if we had used other value for epsilon, we may have jumped over the minimum value of the function, so using the smaller value for epsilon is advised. Minimizing functions with multiple inputs is done similarly to the previous example, but with subtle differences. Instead of the derivative, we will have to find the partial derivative for every input. Partial derivative tells us how changing that input will change the value of the function, similar to the previously discussed derivative. Also, we will not be using the sine function, so instead of changing the input by epsilon, we will be changing every input by the scaled version of epsilon. Let's do one iteration of gradient descent for a function with multiple inputs, which sums the squares of its 2 elements. We find the partial derivatives for every element, and are ready to use the formula. Let's start minimization from the point 1, 1, at which our function evaluates to 2. We see that the first iteration indeed gave us a new input that decreases the value of the function. More iterations would get us closer to the minimum value of this function.